we started discussing about this half-leg T-type topology. So this is also known as neutral point pivoted topology. So this can be compared with diode clamped multi-level inverter and also can be compared with active diode clamped multi-level inverters. Right. So here the topology is something like this. So you have two DC sources. So that means we have an access to this midpoint of this DC source. So how this access is obtained? So by using these bidirectional switches. So these bidirectional switches are connected between this A phase, right? A phase point and this midpoint of this DC bus, right? At the midpoint of this DC bus. So this is how it is connected to the A phase, and this is how it is connected to the B phase. Similarly, so this is connected to the C phase. So we already studied about this bidirectional switches. We already studied about these bidirectional switches. These are known as 4-quadrant switches, and we normally use most of the cases. We can use this RB IGBT, so that's a reverse blocking IGBT. So that can be used, or we can use common emitter based anti-seize connection of IGBTs along with their anti-parallel diodes. All right. So this can be explained, right? So by measuring the voltage between this A and 0. So remember, so these are two IGBTs, right? So the firing signal for the two IGBTs is same. The firing signal for these two IGBTs are same, right? So now, so we'll try to explain its operation. So when this upper switch is on, okay, so when this switch is on and this switch is off, so what is the voltage across A and 0? So when S1A is on, what is VA0? When S1A is on, what is VA0?
VDC2.
This voltage, so let us assume this is VDC and this is also VDC. So this is VDC, right? Similarly, so when this bottom switch is on, so that means S3A is on. So what is the voltage? So what is the voltage VS0?
Minus VDC. Minus VDC.
Minus VDC, right? Similarly, this S2A, so that is the bidirectional switch is on. So what is the voltage?
0.
So what is the voltage VS0? If the
Zero.
bidirectional switch is on, what is the voltage VS0?
0, sir.
So its voltage is 0. So that means it is producing 3 voltage levels. That means it is producing 3 voltage levels, right? Okay. So now the thing is that, so if we compare with the diode clamped multi-level inverter, okay. So here to obtain a voltage of VAZ, so which is equal to E voltage. So how many switches you need to turn on? How many switches you need to turn on to obtain E voltage across A and Z? How many switches we need to turn on here to obtain A and Z?
2 switches.
These 2 switches we need to turn on, right? Okay. So you need to turn on S1 and S2 together to obtain a voltage of E. Similarly, for negative voltage, you need to turn on this S3 and S4 switches. But the thing is that, so here, so in this particular case, you need to turn on only one switch. Okay. So you need to turn on only one switch to obtain a plus VDC voltage or minus VDC voltage, right? So that means when compared to this diode clamp, so here the switching losses are reduced. Agree? So here the switching losses are agreed. So at this point of time, or when it is obtaining this plus VDC or minus VDC, right? Similarly, so here, so if you observe that, so this is a bidirectional switch, similar to this active clamp, right? So this is the one that is discussed, right? So here it will allow the current in both directions. So it is allowing the current in both directions. So that means in the same manner, so this is also allows the current in both directions, right? So depending on that, so you can control this one or you can control this one. All right. So we can control the current in either directions. So therefore, the capacitor's balance can be achieved. So we can achieve the capacitor balance. So that is the one of the advantage. So with this T-type topology or this off-like T-type topology. So one is the conduction losses are reduced, and another thing is, what is another thing? So we can achieve the capacitor balance with this. Okay. Right. So what is the disadvantage here? Right. So when this switch is conducting, okay, or for example, if you want to calculate the blocking voltage of this switch, so blocking voltage means the switch must be off, right? If the switch is off, there are two scenarios. So that means this switch is on and the switch is off. Okay. If the switch is on, so what is the blocking voltage of the switch? What is the blocking voltage of the switch? Our objective is to find the blocking voltage of the switch, right? So here, so the switch is off. Whatever the peak voltage that appeared across, that means, so that we will finding out, right? So there are two possibilities. This is on and this is off. So in this particular case, so what is the blocking voltage here? It's supposed to block this voltage, right? Agree? Agree? Why? Because this voltage, this point is, this is on, right? So that means this point is connected here and this point is connected here. So therefore it's supposed to block only the upper capacitor voltage. So now, so there is another case. So this is off and this is on. So now tell me, what is the blocking voltage of this device, upper device?
2 VDC.
So it's supposed to block this voltage and this voltage, right? So why? Because, so this is connected here and this point is connected to A. So that means, so entire 2 VDC it's supposed to block, or entire 2 capacitor voltage it's supposed to block, right? So now tell me, ideally or theoretically you have only one device, but so when you are implementing that, so in one case your blocking voltage is VDC and the other case its blocking voltage is VDC. So therefore only when you are talking about the blocking voltage, we need to consider its peak value. So that means this device is supposed to block 2 VDC voltage. Okay. So even though it looked like only one device, right? It looked like one device, but practically, so you need to replace with 2 devices. Understood? Clear? So even though you have only one device, it looks like, so but we replaced with 2 devices here. So this is about the blocking voltages of these devices. Okay. So it is 2 times the, or it's supposed to be replaced with 2 devices. Okay. But if you are choosing a higher voltage device, so in that case, the conduction losses will be reduced. All right. So another thing is that, so what is the blocking voltage of this one, this entire unit? So what is the blocking voltage of that entire thing? So again, you have 2 options, right? So when this is on, so what is its blocking voltage? This is off. So what is its blocking voltage in this particular case? What is the blocking voltage of this entire unit?
VDC.
VDC.
So it is VDC, right? It's evident that. So this is VDC. Similarly, so this is off and this is on. So this is off and this is on. Right. So where we are, so yeah, this is off and this is on. So what is the blocking voltage of this one? So what is its blocking voltage?
VDC.
Yes. Its blocking voltage is VDC, right? Agree? Agree? So this is on, right? So that means this is off. So this point is connected here. So that means it's supposed to block VDC. Understood? Right? So now come to, so that means what you understand that, so this entire unit is supposed to block VDC. Okay, so this entire unit is supposed to block VDC. So what about the individual ones? So what about the individual ones? Right. So this entire thing is, see here, if you observe that, so one diode and one switch will conduct, right? So here also one diode and one switch will conduct. So that means, so this entire thing, so can we write like this, VDC by 2 and this is VDC by 2, agree? Agree? So VDC by 2 and VDC by 2. Clear? Okay. So this entire unit or this entire switch is supposed to block VDC voltage. But whereas this main switches or this main one so is supposed to block 2 VDC voltage. All right. Okay. So from this, so we can calculate the device blocking voltage. There is new term, so that is device blocking voltage. So this is the sum of the blocking voltage of all devices. Sum of the blocking voltage of all devices, so that is known as device blocking voltage, right? So in this particular case, if you assume that each source is E, right? If you assume each source is VDC, so what is its device blocking voltage? This is 2 VDC and this is 2 VDC, right? Okay. If we treat this as a single unit, so this will be VDC. Agree? So how much this is? 2 VDC, 2 VDC. So this is 5 VDC per phase. Understand? So it is 5 VDC per phase. That is the overall device blocking voltage. So whereas here, so when come to this, so what is the blocking device blocking voltage here? So this is VDC. So this is VDC. So this is VDC and this is VDC. So whereas this one, so this is also VDC, right? In 3 level. So this is VDC. So how much it is? So it is 6 VDC by 6 VDC per phase. Agree? Agree? So the device overall blocking voltage is 6 VDC by phase. All right. Okay. So now if we compare side by side, so in this, so if we compare with diode clamp, so DC MLI one side, and so this is another side off leg. So how many devices are required per phase? So 4 active switches and 2 diodes are required. So here, so even though if you compare this treated as E2 switches, so that means you require So here you require 2, that means 4 devices. Okay, so 4 devices if we assume that the batteries are same, or else you require 5 devices. Okay, so if you treat, so this switch has 2 switches and this switch has single switch, so that means it will be 5 devices depending on so how we actually are selecting the devices. Okay, so it may be 4 active switches or 2 devices, right? The thing is that so when compared to the diode clamped multi-level inverter, and moreover the additional thing is that so this is how many gate driver circuits you require, how many gate driver circuits you require. So here so you require one gate driver here, another gate driver here, and another gate driver. So that means 3 gate driver circuits are required. So whereas in diode clamp, so you have 4 active switches, you require 4 active 4 gate drivers are required. Okay, so come to losses, right? So come to losses. So here only one device is conducting. So whereas in that case, so 2 devices are in conduction. Okay. So compared to that, so losses are decreased, and the cost wise, so that is also decreased. So additional advantage here is so we can control the capacitor voltages, or we can regulate the capacitor voltages. So that's why so when compared this diode clamp, so this is a definitely a better alternative. This T-type, half-life T-type is definitely a better alternative. It's clear? Understand? So now if you go for higher levels, say for example 5 level, is my voice is audible to you or disturbance system?
Audible, sir. Audible, sir. Audible, sir.
So this is how to design an external circuit or how to balance the capacitor voltages in case of 5 level. Okay. So far we studied for 3 level, right? So now what to do in case if we have 5 level, right? So somehow, so this is a 5 level active rectifier applications. For example, so this is connected to, for example, this 6.6 kV. So grid it is connected by using this coupled inductor. So we'll get back to this in later classes, right? So here we have 4 DC sources. Okay. So in case of 5 level, so you have 4 DC sources, right? So this is, for example, this is ranging from plus 6 kV and this is minus 6 kV. So this positive DC bus and this will be the negative DC bus, right? So this entire thing, so that means 6 minus 6. So that means this entire thing is 12 kV, right? So this is shared among the 4 DC sources. So that means each one is roughly 3000 volts. So each capacitor is supposed to maintain 3000 volts. Okay, right. So now, so how to balance this one? So how exactly balance this one? By using the chopper circuit, that one, so that we discussed, right? So here, so how to balance this one is the simple thing. So here upper one is separately controlled. So here it is something like this. So upper one, so we have some external circuit. So this is the external circuit to balance the upper capacitors. Similarly for bottom one, so it will be like this. Right. So upper 2 capacitors are controlled separately and the bottom 2 capacitors controlled separately. The logic is same here, right? So the logic is same here. So once this capacitor voltage is excess, the power is transferred here So once this capacitor voltage is accessed and this power is transferred, so in this case, all right. Similarly here also, so once this capacitor is accessed, so this is transferred to this capacitor or the upper capacitor. So depending on the requirements, depending on the voltage levels. Okay. So everything is same, right? So everything is same. Only difference is, right? So only the difference is, so what is the blocking voltage of this particular device? What is the blocking voltage of this particular device? What is the blocking voltage of particular device? What is the blocking voltage here? If this device is on, so that means if this device is on, right? So what is the voltage supposed to block? How much voltage is supposed to block?
6 kV. 6 kV.
If this is off, right? Okay. And this is on, so what is the voltage is supposed to block this device?
6 kV.
Yeah, 6 kV. That's you're correct, right? So that means it's supposed to block. So this entire two voltages, right? Agree? Agree? So that means voltage between, so usually we denoted with, so this is M, P1, so this will be P2, and this will be this will be N2. So that means it's supposed to block the voltage between this M and P2. Similarly, so here also, so each device is supposed to block the voltage between this M and N2. So the bid point and the positive or DC, positive or negative DC rails is supposed to block. Okay, so that means each device, even though it looked like a single device, so but it is replaced with two devices here, something like this. Okay, so that's why, so these balancing circuits are expensive. So these balancing circuits are expensive, right? So here, see here, this how many is, it's almost, so 8 devices additional. So that means on cost of additional one phase leg, so it's supposed required. So along with that, you require some inductors, right? Along with that, you require some inductors. So this will increase the cost and as well as weight of the converter. This will increase the cost and as well as weight of the converter. Okay. So that's why most of the applications, so we are limited to 3 level. So most of the applications, so we are limited to 3 level. All right. So however, there are some advantages. So when you're using for, so diode clamp multi-level inverter, for example, for high power applications. So where we, for example, if it is a 6.6 grid is there, okay. The grid is also 6.6 kV. So if the converter is also, so same voltage level. So if you have 6.6 kV, so directly we can connect this converter, so without using a transformer. So without using transformer, so we can directly connect to the converter. So that is known as transformerless grid connected applications. Transformerless grid connected applications. The idea is, so grid is having some voltage, for example, 32.62 kV grid is there, right? So that means we need to, right? So what normally earlier days, what we had to do is we need to use lower, this is 13.2 kV, so maybe 2.3 kV. So that means the rating of the converter is 2.3 kV. So now with these all these things, so we can directly, so bring the converter to match the grid voltage levels, so we can bring it right. So without using transformer, so we can directly connect this way. So most of the cases, so we eliminate the transformer, because the transformer, so most are around, for example, this entire thing is for example, it's 400 kg, 4000 kg weight, or 4 metric tons. So in this 50% of that, so it will be cost of the transformer. So transformers is weighing up to 1500 to 2000 kg. Okay. So we can reduce the cost, as well as we can we can reduce the footprint. Okay. So that is the advantage of grid connected inverters, so without using the transformer. Okay. So this is the fundamentals of the multi-level inverters, right? So in next class I will stop here, right? So because a lot of disturbance is coming out. So next class we'll start with the grid integration. So how to integrate the converters into the grid. So how we'll integrate into the grid. So how to control active power, reactive power, and the voltage. That we'll see in the next class. Okay. So we'll stop here. If you have any questions, you can ask me.